So, hello everyone. Hello everyone. I'm audible. So, I am audible, right? Vivek, Vignesh, Teja, Harshali, Avyashri. All right. So, let's start. So, welcome you all to iitiansgateclasses, and this is in brief about myself. So, myself, Dinesh, and I'm organizer, chief educator at IGC. So I passed my GATE in GATE 2009 with AR 41, and further I pursued my master's at IIT Madras. This is about my teaching experience, and this is about my industrial experience. Okay. So today's session is for mechanical vibration, and mechanical vibration is in syllabus for GATE Aerospace as well as GATE Mechanical Engineering. Now in today's session, I'll be covering damped free vibration, and I will be covering everything from damped free vibration as per GATE syllabus. Okay, and after this session, you guys will able to solve every questions from damped free vibration, hoping for same. So syllabus and references. So what is the syllabus? So syllabus, if you take GATE Aerospace, so the first topic from syllabus is what? Undamped free vibration. Then second topic is damped free vibration, which we are going to cover today. The third topic is forced vibration. And these topics are also common with mechanical engineering. So if you learn GATE mechanical engineering, these topics are common. But in GATE AE, there are two additional topics. Okay. One is what? 2 degree of free vibration. So 2 degree of free vibration, and then continuous system. So vibration of continuous system, free vibration of continuous system. So these are two additional topics in GATE Aerospace syllabus. Now, what are the references we follow? So guys, we follow strictly two references. One is S.S. Rao, Mechanical Vibration by S.S. Rao, one of the best reference book. Okay. So, and the second is Mechanical Vibration by Grover. Okay. So these two are references. Now, first we need to know some basics, okay, before going to demo sessions for damped free vibration. So, fundamentals of vibration. So, basically, vibration is what? So, vibration is what? A motion which is like to and fro motion, right? What is the vibration, guys? A system or a body is said to be vibrating if it has a to and fro motion. Like you guys know, the simple example, pendulum, right? Now, pendulum can do motion about this reference, right? So, this is what a vibratory motion. to and fro motion about a reference is what? Vibratory motion. Okay. Now guys, when you have a free vibration, when you have a free vibration, if a system is vibrating on its own under no influence of force, then the system is known as what? Under free vibration. Okay. So the frequency associated with free vibration is known as natural frequency, or it is also known as natural vibration. Okay. Now what is the damped vibration? When there is a damping, so there will be what? Loss of energy. So when the energy of a vibrating system is gradually dissipated by friction or other resistances, like viscous damping. Most of the mechanical system uses viscous damping. So what will happen? After some time, the system may come to rest. So the vibration are said to be gradually or said to be damped, and gradually this vibration the gradually vibration pose and the system rests in its equilibrium position. So gradually your vibration will be decreases and the system will come to rest. Okay, to equilibrium to equilibrium position. So that is what? Damped vibration. Then there is a forced vibration. So the vibration under the influence of external excitation is known as forced vibration. Okay. Now guys, another thing which is very important in vibration is what? Natural frequency. So what is the natural frequency, guys? Natural frequency is known as dynamic characteristic of a system. It's what? Dynamic characteristic. Natural frequency is what? Dynamic characteristic of a system. Okay, and it is independent of load, and natural frequency is what? The frequency of the free vibration or natural vibration. Now guys, for a single degree of freedom system, what is the equation of motion? Mx dot double dot plus kx equal to 0. So what is the natural frequency of the system? It is under root k by m, and this is what? Single degree of spring mass system, right? Like you have this system, right? So this is mass, this is the spring. So what is the natural frequency? Under root k by m. So this natural frequency is what? Independent of the load or excitation. Also it is known as dynamic characteristic of the system. Okay. So this is about natural frequency. So now we will jump to today's topic, which is what? Damped vibration. So there are different kind of damping. So what are those different kind of damping? One is viscous damping, dry friction or Coulomb's damping, and structural damping. Most of the literature discuss in depth this more of viscous damping, or if you take any Indian author book, they mostly highlight only viscous damping. But if you refer standard book like S.S. Rao, they equally cover well about dry friction or Coulomb's damping or structural damping and other things. But most of the gate question, either it is in gate aerospace or in gate mechanical, they were asked from viscous damping alone. Asked from viscous damping. Okay, so we will discuss today more about viscous damping. So what is the viscous damping? This is the most important type of damping and occurs formally with velocities in lubricated sliding surfaces or dashboard with small clearances. So most of you know, right? The piston, right? Engine piston system, right? So the piston, right, do a motion, right? So there will be a lubrication, right? So this under the lubrications, or you can see the shocker, the the shockers of the automotive, right? Automobiles shocker. So shocker undergo vibratory motion, but there will be what? There will be damping due to like liquid, right? Yes or no, guys? So that is what? Viscous damping. Now guys, we can understand viscous damping by a simple example, like there is a fixed plate and in between there is a liquid and there is a moving plate with some velocity v, which is what, x dot. So there will be a resistance force, okay, due to this liquid, which will be what, some c times x dot. Okay, so what is the c? So c is coefficient of damping. It is known as coefficient of damping. Okay, and this is c is known as coefficient of damping, and it is given by what, mu a by t. Now what is the mu? Mu is coefficient of viscosity, a is what, area of the plate, and t is what, thickness of the liquid. Okay, so this is what, viscous force, F equal to Cx dot. So this is whole about viscous damping. Now guys, we can discuss is next, which is very important, is what, equation of damped free translational vibration. Why I have written here translational word, that is also very important. Guys, most of the literature or the teachers, okay, they will discuss in depth about only translational damping part, okay, or damped free translational vibration. But there can be damped free rotational vibration, there can be damped free torsional vibration also. So whatever the equation which we use for translational vibration, same we cannot apply for rotational or torsional vibration. Okay, so guys, if any doubt, any concern, you guys can tell me. Any doubt or any concern, guys? Okay, so you guys can see there is a spring mass system with damping C, okay, and K is the stiffness of the spring and this is the mass. Now guys, this mass is moving from this equilibrium position by some distance x. So there is a velocity, okay, and acceleration, okay, they are in this direction. Okay, now guys, if you take free body at some distance x, at some displacement x, so if you can see the velocity is in this direction, inertia is in this direction, okay, sorry, acceleration is in this direction, so you know spring force will oppose this displacement, so it is kx in opposite direction, and we know due to damping there is a damping force which is opposing the motion, and same time inertia will oppose also motion. So there are three forces which are all are in opposite direction of motion. So what will be the equation of motion from this free body diagram? Mx double dot plus Cx dot plus Kx equal to 0. Okay, so this is what equation of motion. Okay guys, now guys, we know it is a differential equation of second order. So what is the solution for this equation? Can anyone tell? Mr. Ravi, what is the solution for this equation? What is the solution? The solution for this equation is given by what? X equal to e to the power st, which we know from mathematics, right? Then when we substitute x equal to e to the power st in this governing differential equation, what we find? Ms square e to the power st plus c s e to the power st plus k e to the power st equal to 0, right? So I can take e to the power st common. So what equation I get? Ms square plus cs plus k, then e to the power st equal to 0. Now this is nothing but x. So this can't be 0. So what is 0? Ms square plus cs plus k equal to 0. So this is known as characteristic equation of this damped free vibration under viscous damping. So this is known as characteristic equation. So what is this? It's a quadratic equation. So it will have two roots. When we solve, there will be two roots. Okay. So what those roots are given by, so S1 comma 2, what it will become? Minus C by 2m plus minus under root C by 2m whole square minus K by m. Okay. Now, for these two roots, if you write a general solution for differential equation, so what will be the solution? X will be C1 e to the power s1t plus c2 e to the power s2t. What is this s1 and s2? These are the roots of characteristic equation. What is c1 and c2? c1 and c2 are constants. How we find the value of c1 and c2? Can anyone tell? How we find the value of c1 and c2, guys? Anyone? How do we find the value of C1 and C2? Yes, using not boundary condition, using initial condition, Mr. Ravi, not boundary condition. We find the value of this C1 and C2 constant using initial condition. What is those initial condition? Can anyone tell? What is those initial conditions? So initial condition means what? At t equal to 0, what is your displacement and what is your velocity? So these are your initial conditions. Okay. Now guys, we need to find what next? Critical damped coefficient. Okay. What is your critical damped coefficient for translational vibration? So guys, if you check the root of characteristic equations, those can be what? Those can be real, those can be imaginary based on those based on this equation. But if your roots are real and equal, if your roots are real and equal, okay, so in that case what is going to happen? This second part of this characteristic root will be equal to 0. So in that time your C is nothing but your CC. So if the roots of characteristic equations are real and equal, then your damping coefficient is known as critically damped coefficient. Okay, so that means your Cc by 2m whole square minus K by m is equal to 0, and then you can write Cc by 2m is under root K by m, and we know under root K by m is what? Natural frequency. So Cc by 2m is equal to omega n, or you can say critically damped coefficient is nothing but 2m omega n, or it is also written as 2 under root K by m. Now guys, from this formula there are several gate questions. There are several gate questions based on this formula, single formula alone. Okay. Now the next important thing in damped free vibration is what? Damping factor or damping ratio. So what is this damping factor or damping ratio? The ratio of damping coefficient to critically damped coefficient is known as damping factor or damping ratio. It is denoted by zeta. So zeta is nothing but your C by Cc. Damping coefficient to critically damped coefficient is known as damping factor or damping ratio. Now guys, if zeta is greater than 0, it is known as overdamped. If zeta equal to 1, it is critically damped, and if zeta less than 1, it is underdamped. So you can see when zeta is greater than 0, when C is greater than Cc and zeta is greater than 1, system is overdamped. If C equal to Cc, zeta is 1 and system is known as critically damped, and C is less than Cc, so zeta is less than 1 and the system is underdamped. Now guys, tell me, in general, in any mechanical system, which is preferred among these three? And usually the system will be what kind of among these three in general? Prithviraj, Ravi. Guys, those who are watching on YouTube can also answer. Yes. So any mechanical system which is designed is usually critically damped system. Can you tell, Mr. Ravi, why it is critically damped? Ashali, why it is critically damped? Yes. See, if your system is underdamped, the motion will be oscillatory motion. So we don't prefer oscillatory response. Okay, whenever a system is designed, the system should not have oscillatory response. If system is overdamped, it will take more time to come to rest. So for critically damped system, the system will come to rest with minimum time. Okay, so that's why most of the mechanical systems are designed for critical damping. Okay. Now guys, based on damping, we will see how the responses of the system. So first, for our damped system, zeta is greater than 1, and what is the general solution for equation of motion for our damped system? The response is given by this equation, which is what? C1 e to the power minus zeta under root zeta square minus 1 into omega n1, omega nt plus C2 again e to the power minus zeta minus under root zeta square minus 1 into omega nt. So what is here C1 and C2? C1 and C2 are again constants and can be found from initial condition. For an initial condition where your x equal to capital X, the initial displacement x naught, and your initial velocity is 0. For that initial condition, your response is given by this equation. Now, if you look this equation is exponential. This equation is exponential in nature. Okay, so this is the response equation. Okay. More the damping, more will be sluggish motion. And guys, if you plot this our damping part, you can see more the damping. You can see if the damping is infinity, you have a horizontal line. Okay, the system will never come to rest. If you have more damping, it will take more time, and the least time when it is a critically damped. Okay, so critically damped. Now you can see, so these curves the system comes to equilibrium position in nearly exponential manner. Okay, and higher the damping, more sluggish is the response of the system. And this may even be seen physically that higher the damping, more resistance to the motion, and therefore slower the movement. So the more is the resistance, slower will be the motion. Okay. So this is for our damped system, guys. So any doubt? Any doubt, guys? Any concern? No, right? Now, theoretically, for our damped system, it will take infinite time to come to equilibrium position. Once it is disturbed from, okay, it theoretically your system will take infinite time, and this type of motion is called a periodic motion or non-oscillatory motion. So for our time, system will be having a periodic motion or non-oscillatory motion. Now, next is what? Critically damped system. So for critically damped system, we know zeta equal to 1. So when zeta is equal to 1, if you go to your characteristic root equation, your S1 will be equal to S2 and it will be equal to what? Minus C by 2m, and this C will become Cc. So my minus Cc by 2m is nothing but minus omega n. Okay. Now guys, for this, if you see the solution, general solution, it is given by C1 plus C2 into T e power minus omega n T. Now guys, now here again C1 and C2 are constants and can be found from what? Initial condition. Now if your initial condition at t equal to 0, x equal to capital X naught and x dot velocity is 0. What is the solution? It is given by x naught into 1 plus omega n t e power minus omega n t. Now guys, again if you see this response is exponential and it is non-oscillatory response. Now critical damping is what? Smallest damping for which the system will have non-oscillatory motion. If any damping lesser than critical damping will have what? Oscillatory motion. And with critical damping, system will have stiff fall in displacement or system will take minimum time to come to rest. Okay, so that's why this critical damping is preferred for any of the mechanical system. So any doubt till now? Vignesh, Ashali, others? Any doubt, guys? Those who are watching sessions? Okay. Okay. So let's move to next, underdamped, which is more important for gate point of view, because there is one concept called logarithmic decay, which is associated with underdamped system. So what is the underdamped system? If zeta is less than 1, then system is known as underdamped. Now for underdamped system, the general solution is given by what? This is for characteristic roots. So your characteristic roots are given by this equation, okay, and we know if zeta is less than 1, so you will have what? An imaginary term also, and when you have an imaginary term, the general solution will be given by this equation, which is what? E to the power minus zeta omega n t, and then C1 e to the power iota under root 1 minus zeta square omega n t, and this. Now guys, for this, again C1 and C2 are constants and can be found from initial condition. And when you have this initial condition where initial displacement is non-zero and velocity is 0, the response is given by this equation. Now guys, if you see this equation has sinusoidal term. So the motion will be oscillatory, and in this equation what? This is known as amplitude of vibration. This is what? Amplitude of vibration. Now if you see the amplitude of vibration, it is exponential. It is what? Exponential. Okay, so this is what amplitude of vibration. And what is this phi? Phi is the phase angle. It is given by what? Tan inverse under root of 1 minus zeta square by zeta. Now guys, for underdamped system, the natural frequency is known as what? Damped natural frequency, and it is given by what? Omega t. It is what? Under root of 1 minus zeta square into omega n is what? Your damped natural frequency, guys. Okay. Now if you see the response, response for underdamped system, you can see it's an oscillatory response. Theoretically, system will never come to rest for underdamped system. Okay, theoretically system will never come to rest. Okay, but in actual, in practical, the system will come to rest after some time, because there is a gate question in GATE 2023 based on these conditions. Okay, based on these condition we will solve that question, then we will come to know what actually that question is. Now the next important concept in this is what? Logarithmic decay. What is the next concept, which is again very important concept from GATE perspective, is what? Logarithmic decay. What that? Logarithmic decay. So guys, what is the logarithmic decay? It is defined as what? It is the ratio of any two successive amplitudes for an underdamped system vibrating freely is constant. It is not that. It is actually logarithmic decay. Delta is what? Ln of the ratio of two successive amplitude. Like it is x1 by x2. Okay, and it is a function of damping only. So guys, here the first amplitude you can see xa, and the amplitude of next cycle is xb. So what is the delta? If I define here, it is ln of capital X by capital xb. Okay, now guys, what is this ln? It's a natural logarithm. Okay, or you can say delta is given by 2 pi zeta under root 1 minus zeta square in terms of damping. So it's a function of damping also. Now zeta is also written as what? 1 by n ln of x naught by xn. Now guys, what is the n? What is the n? What is n here? N is number of cycle. What is the n, guys? Number of cycle. So how you define number of cycle? It is always like nth cycle minus first cycle. Okay, it is always nth cycles minus first cycle. Now, or you can say it is not like that. Better way to say it is nth amplitude minus initial amplitude. Now you can see nth amplitude is what? N. What is the initial amplitude? It is 0. So the number of cycles are n. Because guys, in many GATE question, the students will have confusion when the question is asked how many cycles. Okay, we will see that question also. So after logarithmic decay, the next concept is what? Is energy dissipation in viscous damping, because there is one question from that also. So the total energy dissipation in viscous damping in a cycle is given by what? Pi c omega d x naught square. What is the x naught? Amplitude, initial amplitude. Okay, initial amplitude of the vibration. What is the omega d here? It's a damped natural frequency. Damped natural frequency. What is the C? It is a damping coefficient. What is the C, guys? It's a damping coefficient. Okay. So any doubt, guys? Anyone have any doubt till now? Okay. If no doubt, we will move to next part. Yeah. So most of the people, they cover, as I told, translational damped free vibration. But very less people talk about this torsional or rotational damped vibration. So in case of rotational vibration, you can see this is theta is what rotational displacement, theta dot is rotational velocity, and theta double dot is acceleration, angular acceleration. So you can see you will have the forces, inertia force, which will be J naught theta double dot in the opposite direction of the motion. Then this is what spring force, which will be again in the opposite direction, and this is due to velocity. So what will be the equation of motion? It will be J naught theta double dot plus Ct theta dot plus Kt into theta. Okay. Now guys, what will be the natural frequency in this case? The natural frequency omega n will be under root Kt by J naught. Now guys, what will be the zeta, damping ratio, damping factor? What will be the zeta? Guys, usually people write C by Cc. It is not C by Cc in this case. It is what? It will be Ct upon Ct critical. So what is the Ct critical? It is Ct upon 2J naught omega n. So guys, instead of 2 omega n, it is what? 2J naught omega n. And instead of C, it is what? Ct. Okay. So this is very important. And same way, guys, if your motion is rotational, in that case also your zeta will not be simply C by Cc. It will be what? It will be C rotational upon C rotational critical. Okay. For rotational vibration also, guys, for rotational vibration, your zeta will be what? C rotational upon C rotational critical. Okay. So that's about torsional and rotational vibration, equation of motion, and then natural frequency and damping ratio part. So any doubt, any concern? Mr. Ravi, you know, right? Everywhere student study till translation, damped translational vibration, right? So this is the additional part we cover, and there are good gate question from this concept. Clear? Okay. Yeah. So let's move to next is what? So that's all about viscous damping, and I have covered all the concepts related to viscous damping that are asked in GATE exam. Okay. Now we will be discussing in brief Coulomb's damping. So from Coulomb's damping, actually there is no question in GATE mechanical, but in GATE aerospace also only one question, and that too directly related what is the natural frequency in case of Coulomb damping. So in case of Coulomb damping, natural frequency will be independent of damping, means your natural frequency remain same. Okay, in case of Coulomb's damping. So basically, what is the Coulomb's damping? The damping produced due to friction is what? Coulomb's damping. So it is also known as dry friction damping or Coulomb's damping. When you can see, suppose a system is oscillating on a rough surface, so there will be force due to friction, which will be opposing the motion, is what? F equal to mu Rn. What is the Rn? It's a normal force and it is given by what? Mg. So what is the friction force? It is mu Rn or it is mu Mg. So this will be resisting force. So in case of Coulomb's damping, there is a loss of amplitude. So what is the loss of amplitude in one cycle in case of Coulomb's damping? It is given by 4F by K. So 4F by K is what? Total loss of amplitude in one cycle. What is the F? F is the Coulomb's force, okay, which is mu Rm or mu Mg. What is the mu? It is not coefficient of viscosity. It is mu is here what? It's a friction coefficient. It's a coefficient of friction. Okay, so that is about Coulomb's damping. So these are the few points about Coulomb's damping which anyone can refer. So the equation of motion is non-linear with Coulomb's damping, where it is linear in case of viscous damping. The natural frequency of the system is unaltered with the addition of Coulomb's damping. But in case of viscous damping, your natural frequency will be changing, or the frequency of the damped free vibration will be different. Now the system comes to rest after some time, okay, after some time in case of Coulomb's damping. But in case of viscous damping with underdamped system, theoretical system will not come to rest. Or in case of okay, now the fourth part, the total loss of amplitude is 4F by K in case of Coulomb's damping. But in case of viscous damping with underdamping, we have seen the logarithmic decay of the amplitude. So that's about Coulomb's. Now the last part is what? Structural damping. So structural damping is usually due to intermolecular forces. So whenever the system is loaded, the loading and unloading will be different. So there will be during loading and unloading, there will be a dissipation of energy, and that energy will be stored in form of hysteresis loop. Okay, so that is what? Structural damping, okay, due to intermolecular forces. Now we can see stress-strain diagram. So there is a hysteresis loop. So there is a molecular friction per cycle per unit volume. So that's all about, theoretically for gate perspective, either gate mechanical or gate aerospace structural damping part. So any guys, any doubt or any concern? So we have discussed all the concepts related to damped free vibration for gate aerospace and gate mechanical. With these many concepts, you can solve any questions from previous year's paper. So let's start with GATE 2023 question. So what is the question? What it says: which of the following statement is or are true about harmonically excited forced vibration of a single degree of freedom linear spring mass damper system? So guys, this question is partially related with damped free vibration as well as forced vibration. So I will just write the equation of motion for forced vibration, which is mx double dot plus cx dot plus kx equal to f naught sine omega t. Now what is the solution for this equation? It will be given by x equal to xc plus x pi. So there are two parts. One is a particular integral, or I can write better in terms of like pi plus cf, complementary function and particular integral. So one is related with damped free vibration and one is with there are steady state part and transient part. So the steady state part is with particular integral, okay, and complementary function is related with transient part. So read the options. What it says: a total response of the mass is combination of free vibration transient and steady state response. So that is what particular integral is related with steady state response, and this is what transient part, which is related with complementary function. So option A is correct. The free vibration transient part dies out with time for each of the three possible condition of damping. So guys, in gate key, they gave B also correct. Underdamped, critically damped, and overdamped. Okay, so after some time, this free transient part dies out. Means your system comes to rest if it is only under damped free vibration. Or you can say this part will become zero. But theoretically, it doesn't. Theoretically, the system will not come to rest. But here they have not mentioned, and they told B is also correct. Yes, B is correct. Practically, system will come to rest under damping. Okay. Now option C read, the steady state periodic response is dependent on initial condition at the time of application of external forcing. No, steady state response doesn't depend on initial condition. Your complementary part or transient part only depends on steady state response. So C is not correct. The rate of decay of free vibration transient response depends on mass, spring, stiffness, damping coefficient. Yes. What is the logarithmic decay we have seen? Delta is 2 pi zeta under root 1 minus zeta square. What is the zeta? It is C by Cc. So C by what? 2m omega n. So you can see it depends on mass, it depends on spring constant and damping constant, right? Right. So C is damping constant or damping coefficient. So D is correct. So A, B, and D are the correct answers. So clear? This question is clear? Yes or no? Prithviraj, it is correct? Clear? Any doubt? Yeah, additional concepts which I have not taken forced vibration, but I have taken this question just to demonstrate, guys, whatever we study in the class or in this session, there will be some related gate question. Okay, so let's move to next question, guys. What it says: a linear mass spring despot system is overdamped. In free vibration, this system undergoes. So what kind of motion? This is another gate question from gate mechanical. So what is the overdamped system? It's a oscillatory or non-oscillatory motion or random motion. We have seen what kind of motion is overdamped. Anyone? What kind of motion is overdamped, guys? It's a non-oscillatory motion, right? Overdamped and critically damped is what? Non-oscillatory motion. Okay. So A is the answer. A is the answer. Now read the next question, guys. What it says: for a damped single degree of freedom system with damping ratio of 0.1, the ratio of two successive peak amplitude of free vibration is. So guys, they given the damping ratio zeta equal to 0.1. Now we know the logarithmic decay delta is what? 2 pi zeta under root 1 minus zeta square, or it is nothing but approximately 2 pi zeta, which is what? It is ln of ratio of two successive amplitude. So it is what? Ln of x1 by x2. Now what is the asked? They asked this ratio of two successive peak amplitude. So x1 by x2 is what? It will be e power 2 pi zeta. Now guys, find out e power 2 pi. What is the zeta? 0.1. Guys, can you tell me what is the answer? Can you guys solve and tell me quickly, Mr. Ravi? So what mistake people do? Instead of finding this x1 by x2, usually people just tell delta. The answer is delta, which is not correct. Quickly guys, solve and tell me the answer. So let me check my answer. So what is the answer? 1.87. Are you sure? So others also please check this answer is correct or not. Okay, you guys can check. Let me move to next question. Yeah. So read this question, Prithviras. Yes, good. Next question, guys. Read. For a damped spring mass system, mass m equal to 10 kg, stiffness k equal to 10 to the power 3 Newton per meter, and damping coefficient c equal to 20 kg per second. The ratio of the amplitude of oscillation of the first cycle to that of fifth cycle is. So guys, in this case, now see what they asked, the ratio of x1 to x fifth. Now tell me guys, how many cycle will have this? How many cycle will have, Mr. Ravi? There will be 5 cycle or something? So what I told, the number of cycle is what? Nth amplitude minus first amplitude, right? So first amplitude is here 1 and nth amplitude is 5. So number of cycle is 4. So what is the delta? It is 2 pi zeta approximately, and this is nothing but what? 1 by n ln of 1 by n ln of the first amplitude to nth amplitude, right? Now guys, what is the n here? 1 by 4. So ln of x1 by x5. What is asked? They asked the ratio of what? X1 upon x5. So what it will be here guys? X1 upon x5 will be 8 pi zeta, right? E to the power 8 pi zeta. Am I correct? Yes, it is e to the power 8 pi zeta. Now, how you will find zeta, guys? Zeta is unknown here. So, zeta is what? Zeta is C by Cc, right? Zeta is C by Cc. Now, guys, C by Cc. So, it is C upon 2 under root Km, right? So, guys, zeta you can substitute here. So, you can write e power 8, so you can write it will become 4 pi upon under root km. So guys, find out value of x1 by x5 in this case. Any doubt or any concern, guys? So what will be the answer? It will be 12.42. X1 by X5 is what? 12.42. So again guys, what mistake people usually do? They will write number of cycle equal to 5. So always guys, you have to find number of cycle correctly, then your answer will be fine. So is it okay? This is correct? Yes or no? So next question guys. Let's discuss next question. Yeah. So this is one of the very good question, and hardly people find the correct solution for this. So what is given in this question? Guys read. Yes. So previous answer is correct. Yes or no? Previous answer is correct. Ravi, yes or no? Okay, okay. Please calculate. Or you can calculate and check. Okay. No problem in that. So we'll move to next question. Yeah. So read what next question says. A uniform rigid bar of mass m equal to 1 kg and length L equal to 1 meter is pivoted at A. It is supported by a spring of stiffness K equal to 1 Newton per meter and a viscous damper of damping constant C equal to 1 Newton second per meter with A equal to 1 upon under root 3 meter as shown below. The moment of inertia of the rigid bar is given Ia about this pivot point ml square upon 3. So what they told, the system is overdamped, underdamped, critically damped and underdamped with these two options they give. So how to solve this question guys? So the first thing, I will draw this system again guys. Okay, so it is like this. There is a spring connected here and there is a damper connected here. Now guys, if you see the oscillatory motion for this system, it will be like this in this plane, something like this. So when in this condition, suppose this is theta, so this is moving in this direction, so this will be what? A theta, and this will be what? L theta. Okay, now guys, when this is moving in this direction, you have theta dot velocity and you have theta dot double dot acceleration. So you will have the forces, spring force, which will be what? K times A theta. Then you will have damping force, which will be what? It will be C theta dot. Okay, this will be spring force. Now guys, there will be inertia, right? So what will be this inertia? It will be in opposite direction of the motion, and which will be what? Ia theta double dot. So now if you see the equation of motion, see this spring force above this pivot point A will give a moment. So what will be that moment? It will be Ka square theta. Same way, this damping force about pivot point this A will give another moment, which will be what? Which will be C theta dot into what? This length L. This length L. Okay, L is the length. Okay, perpendicular length to that force. So guys, if you write now equation of motion, what is the equation of motion? It will be Ia theta double dot plus CL theta dot plus Ka square theta equal to 0. Now guys, I have written what? in case of rotational vibration, what is the natural frequency? What is the natural frequency, guys? What is the natural frequency in case of rotational vibration? What is the natural frequency? It is under root K rotational by J naught, right? So what is the J naught? IA. Now guys, what is the K rotational? It will be nothing but K A square. So what will be the natural frequency? K A square upon IA. Now guys, what will be the zeta? What is the zeta? Yeah, root of K upon I. No, Ravi, it is not K, it is KR. And what is the KR? Clear? That is the mistake. Okay. So natural frequency is what? Under root Ka square upon Ia. Now what is the zeta? We know zeta is what? CR upon CRCC. What is the CR? CR nothing but here CL. So it is CL upon, what is the CRCC? It is 2 IA omega n. Okay. Now substitute everything and find out the zeta value. Now you have everything. You can find first this natural frequency. So which is what? K. What is the K value given? It is 1. What is this A value? 1 by under root 3. So it will become 1 by 3. Now what is the IA? IA is given as what? ML square by 3. What is the L? 1. What is the M? It is 1. Okay. So what we find? We find 1 by 3. So what is the natural frequency? It is 1 radian per second. Clear? So natural frequency came as 1 radian per second. So now substitute here. Now guys, what is the C? C is given as 1 Newton second per meter. So it is 1. What is the length? 1. Now by 2. What is the I? It is ml square by 3. So it is m is 1, L is 1 square by 3 into 1. So what is the zeta? What is the zeta, Ravi? What is the zeta? It is 1.5. It is 1.5. So tell me, what is your system, Ravi? Now, which is the correct answer? Vignesh, Prithvi. What is the correct answer now? A is the correct answer. A is the correct answer. Now, what mistake, Prithvi, people do? It's our damn. What people do mistake? Anyone can tell? Usually, what people do mistake? They write zeta as what? C by Cc. If you write zeta as C by Cc, Mr. Ravi, what is the answer? It is C by 2 under root K by M. What is the C? It is 1, 2. What is the K? It is 1. What is the M? 1. So what is the answer? If you write zeta as C by Cc, what is the answer? Zeta is coming as 0.5. So it is not, it means what? Underdamped, which is not correct. So people will say B is the answer, which is not correct. What is the answer? A is the correct answer. And if you know the concepts of rotational and this torsional vibration for damped, or you can say viscous damped torsional and rotational vibration, then only you can solve this question correctly. So A is the answer. So I think that's all from today's session. And if you guys have any further doubt or concern, you guys can contact to this number. You guys can also follow us on YouTube, Telegrams, and other social medias. We have dedicated channels on YouTube, either for aerospace, mechanical, EC, electrical, and others. You guys can also follow us on Telegram. And guys, IGC teaches not just aero branch, other branches also, and it is advantage because aerospace is a disciplinary branch. And if you guys want to get in ISRO, if you are writing ICRB exam, yeah, IGC can only be the the right option for you guys to choose. Or if you want to go in future, like in data science area, computer, or robotics branch, or in control and guidance. So IGC teaches EC electrical branch also. So we have expertise to guide the students in robotics area or control and guidance. Or suppose you want to work in machine learning or data science, IGC teaches computer science also. So we have that extra, expertise also. So that's all from my side for this session. So thank you all. For any doubt, you guys can reach to me, okay, on IGC forum or anywhere on these given contacts.